All right, here's a problem for you to see if you understand what the term solubility means and what needs to happen when you want to determine the solubility. Because remember, the term solubility refers to the amount that can be solubilized or the amount that can dissolve. So what do you think about this question?
So it says that 39 grams can dissolve in 100 grams of water, right?
That's right. And now we have a different solution that we're making over there where we put 10 grams into 50 grams of water. And we want to know, is our solution, our resulting solution going to be saturated, unsaturated, supersaturated? None of these.
I'm not sure I know how to solve this.
Well, can you see that if we see that 39 grams should be able to dissolve in 100 grams of water, right? 39 grams of NaCl for every 100 grams of water. Whoops. H2O. Then we can just kind of use a relationship here and say that how many grams should I be able to dissolve in 50 grams of water?
Oh, that's just half. So half of 39. What is that? 19 and a half?
Yeah, that's right. 19 and a half. So if we only have 10 grams dissolved.
Unsaturated.
Very good. That means our solution is unsaturated, right? It means we can dissolve more. We can dissolve all the way up to 19 and a half grams. Excellent. So, when you put an ionic compound in water, it does more than what we call dissolve. It also dissociates. Dissociate. Now we're going to look at this word dissociate and understand what it means, what's going on. So this video is going to show us what happens.
Are held together by a track.
Okay, so we've seen this before. We have an ionic compound, and the ionic compound at room temperature resides as a three-dimensional lattice. Do you remember that term?
Yeah, but I couldn't remember it.
Yeah, three-dimensional lattice. So that means all of our ions are interacting with lots of neighboring ions. Now here's what happens when we put a soluble ionic compound into water. The water molecules surround the different ions and supply the charge that their neighboring ions were supplying. So for example, this green sphere here is a chloride ion, and its neighboring sodium ions, positively charged sodium ions, and there would be one in front and one in back and one on the right generally, right? So 6 neighbors. These chloride ions, or these sodium ions, are kind of providing a little bit of positive electron density and pulling extra negative electron density away from the chloride ion, right? These ionic compounds result in these three-dimensional ions, or three-dimensional lattices, because of the charges which are on the individual ions. Well, when you put it into water, what happens is the water molecules, again, surround and remove each individual ion from the total. So when the salt dissolves, it also separates into ions. And there's a term for this separation that occurs when you put a ionic compound into solution. And this term is dissociation. Dissociation. So salt dissolves, but a more effective term for a salt dissolving is dissociation, to tell people that all of the ions are now separated from all the other ions and they're surrounded by water molecules. Okay? Molecular compounds also dissolve, but they don't dissociate because there's no ions to separate and remove from the three-dimensional lattice. Okay? They dissolve the same way. Water molecules surround them and provide the stability for the individual molecule. But again, no ions result. And this can be seen in the electrical conductivity of a solution. Do you remember this?
Yeah, I remember that. If you put salt in water, it makes the salt conductive.
Very good. It makes the salt conductive. And then the conductivity will allow the light bulb to turn on, right? Again, the solution's not making any energy. There's a battery over here that's supplying the power. But if the electrons can flow through the solution, we say the solution is conductive, okay? We have a term for solutions, or compounds. We have a term for compounds that you put into solution that result in conductivity. And we call these kind of compounds electrolytes. And we say a compound that you put into water and ions result, those ions are also can be referred to as electrolytes. Have you ever heard of electrolytes before?
Yeah, I drink electrolytes in my power drink after I'm done doing my power exercises.
Yeah, that's good. Power exercises, I mean, if you use a lot of energy and sweat a lot, you lose a lot of water and also a lot of ions, electrolytes, and so you want to kind of replenish that, right? Now, don't get tricked. I hope you're not tricked, Fred, into thinking that just because there's a lot of sugar that it's helping you out, right? You know that's not true.
Well, what do you mean?
Well, the sugar in sugary electrolyte drinks isn't contributing the electrolytes. It's contributing the well-needed energy often as well. But the electrolytes are really what you want to make sure you get. And electrolytes are just salt. So you can get the electrolytes other ways as well. You don't have to buy the expensive expensive sports drinks, right? Some compounds, you put them into water, like sugar, they are non-electrolytes. So when you put them into water, you don't get a conductive solution. And that's because no dissociation occurs. So there's those two words again, dissolve and dissociate. If a chemical dissolves, that means water molecules surround it and remove it from all of its neighbors. If it dissociates, that surrounding happens at an ionic level. So all of the ions are the individual dissociated, dissolved components. So we have a non-electrolyte, chemicals that don't make electrolytes when placed into water, but we also have what are called weak electrolytes. So the strength of these electrolytes is not how strong they influence you or something like that. It's just referring to to what degree they create ions when placed in solution. And we'll talk about some weak electrolytes coming up. So whenever we see a chemical reaction that a ionic compound is utilized, you'll usually see it in the form of an aqueous compound. Because, again, these things don't react much as solids because most of the ions will be lost inside the particulates or the little granules, right? So we want to familiarize ourselves with the actual ions that are in the compound. And so we can write the dissociation of these ionic compounds like this. So here's an example of our compound. You want to tell me the name of this one?
That's the sulfate, and so sodium sulfate.
Very good. Sodium sulfate. When I put sodium sulfate into water, what I get is 2 sodium ions. You see where we got the 2?
Oh, there was 2 to start with.
That's right, 2 sodium ions and 1 sulfate ion, right? And I also have to recognize that this dissociation results in the sulfate ion, which has a 2- charge. So I'd have to look at my chart if I didn't remember that. I can also always use, or sometimes use, the counter ion of the sulfate. In this case is the sodium. And if we know about the charge of the counter ion, what's the charge for the sodium ion?
It's always +1.
That's right, it's always +1. Therefore, if I know that there was 2 for this 1 sulfate to create this ionic compound, I would know that that way that the sulfate has a -2 charge as well. Okay, sometimes you don't see the aqueous when ionic components are placed or any chemical equations, but that's all right. Don't get too sore. The deal is, if you see an ionic species like this, it has to be dissolved in water, right? Okay. So let's write the dissociation of these compounds, all right? So let's identify the 2 ions, or usually there's just going to be 2 ions, right? Anion and cation. Let's identify the 2 ions and then identify how many of each there are. And let's write their charges off to the right. So what are the 2 ions that we have here in this first compound?
Sodium, you got 3 of them, so 3 Na plus.
Very good, 3 Na plus. And what's the other one?
PO4. Let me look at my table. Oh, that's phosphate.
Very good. Phosphate ion. And what's the charge?
3 minus.
Very good. So those are our ions. See, I have 3 sodiums and 1 phosphate. Very good. So that's the dissociation. How about this? What's the dissociation here? How many ions am I going to get?
You're going to get 2 aluminum with a +3 charge and 1 sulfate with a -2 charge.
Wow, that was pretty good. How did you do that so well?
I used the reverse crisscross rule.
Oh yeah, that's right. Because the 3 here could go up there, and it would remind you that aluminum has a +3 charge, and the sulfate would get the -2 there. Excellent.
I don't think I said 3 sulfates.
I can't remember if you did it either, but 2 aluminums, 3 sulfates, right? Very important to recognize that those are the ions that we're going to get. All right, what's this compound?
Calcium chloride.
Very good. Calcium chloride. Dissociates into what?
Calcium ion and chloride ion.
All right. It's not enough to tell me just what the ions are, though, right? You need to make sure you understand and that you're telling whoever it is you're indicating the ions that result what the charge is on them, okay? So,
Okay, yeah, so it's Ca +2 and then 2 of the Cl minuses.
very good. Excellent. How about this last one? What's this last one?
Let me look it up. It's calcium permanganate. Permanganate.
Permanganate.
Calcium permanganate.
Very good. Very good. And what are the resulting ions?
Calcium with a +2 charge, and then, let me look again. 2 permanganates with the -1 charge.
Very good. Now, you didn't really need to look again at your periodic table, did you?
Why not?
Well, because if you knew that the calcium was a +2 and you saw that there were 2 permanganates,
Oh, yeah.
you'd have to know that the permanganate has to have a -1 charge to be balanced in that ionic compound, right?
Yeah, that makes sense.
Very good. Excellent job. So this is how we show the dissociation of ions. Or in other words, when we think about an ionic compound that's aqueous, we have to know what this means is that these specific ions are separated from each other and being dissolved and chaperoned around by water molecules. Okay? Good job.